Okay. Okay.
Okay, hello everyone. So we'll continue about the topic in the week 9. We talk about the still talk about the time complexity analysis of iterative algorithm too. Okay, so so now what we would like to sharing I would like to sharing to you is that how well how we introduce uh, some error. Oh, okay. Wait a minute. Wait a minute. View. Okay. Sorry. Okay. So actually, we'll have two methods. Okay. To handle how to find the time complexity efficiency in an algorithm. Okay. So let first check the. This is the overview. I would like to further introductions. So the introduction is just a little bit introductions, and the second step is we talk about the sum notation method, and the third step is we would like to talk about the table construction method. Okay, and of course that we have homeworks at the final. Okay. Okay, so before we elaborate the efficiency time of previous algorithm, then we will introduce some notations. Of course, that this is very, for instance, that you have this loop. Okay, how to make this loop become the sum notations. Okay, so simply that if you have something like this, yeah, for I equal 1 to n minus 1, then simply that you need to write sum of I equal 1. Yeah, okay, since that 4 is the increment is 1. Okay, the increment is 1 times plus 1 uh, in one loop. Okay, so I equal 1 until n minus 1. Okay, so since that here here is the operation is one operation, that means this is 1. Okay, so then finally we'll have the sum notations in this 4 is something like this, and then this is the tm. So this is the time complexity. Okay, so then when we have a time, okay, when we have a time efficiency, and then we can rewrite something like this: sum of I equal 1 n minus 1 1. So since that, remember about the sum of I equal a until b1. So it's something like 1 plus 1 plus 1 is equal to 1 plus 1 plus 1. So plus 1. So how many ones? So it should be b minus a plus 1. So it should be equal to b minus a plus 1. Okay. So similarly, so since that a is 1 and b is n minus 1, so it should be b, this is b, and this is a, b minus a plus 1. So this is minus 1 plus 1 is 0, and then it's remain n minus 1. So n minus 1 is in the big O of n. Okay, so finally we will have something like this. So okay, moreover, we can consider two basic rules of some manipulations. So something like this. So if you have something like these notations for I equal k to n, and there is a c is constant. Okay, any constant is not depend on I, so there is no I here. So c can be out of in the sum. So c time it's equal to c times sum of something like this. So or I can write something like this. So this is like I equal k, so it should be okay, so this one. Okay, so this one is c times a k, okay, plus c time a k plus 1 plus blah 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 plus c plus sorry plus c time a n. Okay, so Okay, so and then we can rewrite something like this: C is equal to C times, okay, AK plus AK plus 1 plus blah 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 plus AN. Okay, something like this. So C can out, we can write in the front of sum. Okay, so another one is that if you have a sum of something like this, plus or minus, okay, plus or minus, okay, so then it should be in a linear form. Okay, there should be sum of IK, something like this. Okay, and it's similar to something like this. This is, for instance, this is AB, or this is KN, so it should be is equal to N minus K plus 1. Okay, so something obviously. So if you have a sum something like this is I, okay, single I, that should be 1 plus 2 plus blah 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 plus N. Okay, from I something like 1 plus 2 plus 3 till N, it should be N time N plus 1 over 2. Okay, it should be big N square. Okay, so then then okay, so okay, we see this example. Okay, so we have a function test n, and we have for I equal 1 to n and j equal I, while something like this. Okay, so since that the step is increasing or decreasing one step, okay, one time step, or one number, okay, for every loop, then we can write in the sum form. Okay, so then finally, so first that we need to write, so actually we have two loops. First, this the loop for and the loop while. Okay, so and then we need to write the first loop. Okay, so something like for I equal 1 to n, so this is something like sum I equal 1 to n. And how about this one? So this one, it's similarly. So this is j equal I until j greater than 0. So it's something like sum of j equal I. Okay. So this is until j equal I. This is until 1, right? Okay. So this is greater than 0. Greater than 0 is 1, where j is integer. Okay. So it should be 1. So something like this. Okay. So now we have the Tn, Tn is equal to something like this. Okay. And sorry, and this one, so what it is, so we look at here. So like here we have the basic operation. So this is basic operation 1, and so it should be 1. Okay. Something like this. And then finally, we can write something like this. So what is something like this? J equal I until this one is 1, 1. So this is backward, right? So the sum of backward. So what we can write something like this. Okay. So 1 plus 2 plus 3 plus 4, it should be equal to 4 plus 3 plus 2 plus 1. Okay. Or in the notations, for something like I equal to 1, 4 I, or it is similar to sum of I equal 4, and this is 1. Okay, so which is decreasing, so actually it's similar. Okay, so then we can write in the similar decreasing, increasing, so then it's similar to sum of, so if we have a Tn is equal to sum of I equal 1 to n times, this is j equal 1 to I, okay, n 1. Okay, and finally we have something like this. Okay, so something like this. So we know that something like, if it is 1, so if it is 1, then this loop, okay, so then this loop, we can see that this loop become b minus a, b is I, b minus a minus 1, I minus 1 plus 1. Okay, so minus 1 plus 1 is 0. Okay, so this is it. And now we can just only let something like this. I equal what? And I. Okay, I equal 1 and I. And then what we can do is, this one is similar to this property. Okay, So if you have a I equal 1 to ni, it should be 1 plus 2 plus 3 and etc. And then of course that is 1 plus 2 plus 3 plus n, it should be equal to n time n plus 1 over 2. It should be big O of n square. Okay, so this is very simple. Okay. Okay, now how about this one? Nah. So in this okay, so this is very easy actually. So since that we have 3 1 2 3 3 4, and then you need to write the functions of Tn. Of course that we have a Tn. Okay, so the Tn. So and then it's equal to sum of. Okay, so the first sum is from I equal 1 to n minus 1, and then sum of j equal to 1 to n. Okay, sorry, this is 1 to n. And the third one is sum of k equal 1 to n minus 2. Okay, and how many basic operations? So this is one basic operation and this is one x. So totally two basic operations. So then this is 2. Okay. Okay. So remember that if you have a 2, or we know that 2 is 2 times 1. Okay, so this is 2 times 1. Okay, remember about this. So this is 2 times 1. Okay, it is equal 2 times 1. So 2 is something like constant. Okay, so 2 can be moved to the front. Okay, so it is something like 2 sum of I equal 1 to n minus 1. This is sum j equal 1 to n, and this is sum of k equal 1 to n minus 2. This is 1. Okay, something like this. And then finally we will have something like this. And since that this is 1, and then we use the formula of sum of, remember about a equal a to b. So 1, it should be equal to b minus a plus 1. Okay, so this is the formula, and then something like this. So first sum, okay, in the first sum, so we need something like this. And then this is n minus 2 minus 1 plus 1 should be n minus 2. Since that n minus 2 is constant, so n minus 2 also can move in the front. Okay, n minus 2 is constant. There is no j. Okay, there is no j. So furthermore, that this is similar. This is also the sum of this one, and I can move something like this. Okay, so this is n minus 1, sorry, n minus 1 minus 1 plus 1. Okay, sorry, this is, okay. So this is what is n minus 1 minus 1 plus 1. Okay, since that, uh, sorry, this is n. Okay, wait a minute. Sorry about that. Okay, this is true. Since that this is n, b is n, so this is n minus 1 plus 1. Okay, so this is 1 plus 1. Since that this is n. Okay, so remember that n again, n is a constant. Okay, there's no dependent with I. So then if n is the independent, so then n can be moved in the front. Okay, so something like this. And then we left one sum. Okay, sum of I equal 1 to n minus 1 1. So it is nothing else, is become this one. Okay, so n minus 1 plus 1 should be n minus 1. So okay, so and then 2 times n minus 2 times n time n minus 1, you can get something like this. Which one it is in the big O of n cubic? Okay, something like this. So I think this is very easy in the sum notations. Okay, so there's some remarks. Okay, you should not have the erroneous impression that the plain outline above always success in analyzing iterative algorithm. Okay, and an irregular change in a loop variable a sum too complicated. For instance, that you this is for instance that for instance something like this. So while, for instance, something like this. Okay, while j less than 0, and then j equal to n, something like this, and j is equal to j plus 3, for instance. Sorry, this is minus 3. And what happened? So using sum is, I think it's very difficult. Okay, this is very complicated. So since that sum is only for when in the algorithm is j equal to j minus 1, or using 4 is exactly uh, the increment of 1. Okay, so that or j is equal to j plus 1, something like this. Okay, so if the irregular change, then the sum notation is too complicated. Okay, then and another thing, that this civet notwithstanding, the plan does not work for many simple algorithms. Of course, that for the simple uh, method, that sum is still very useful. Okay, and of course that we need to consider again another method. Okay, so if we want to uh, use to analyze the algorithm when we check irregular step in the loop. Okay, 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 so this is the example. Okay, so example that if you have the binary, remember binary. So so this is the binary. Okay, what the binary of n? Okay, so if n equal to 5, and then find so this is the binary. Okay, the binary number of n, and something like this. So remember that in this while, what we can find here, that n is in irregular. So this is the n will be uh, decreasing. Okay, so 2 times, decreasing 2 times, or something like this, and it's equal to n minus 2. Okay, so then using sum, it is not possible. Okay, using sum is not possible in here. So then we can use a very primitive way when we call that they're using table method. Okay, so what is table method? So we talk about the table method. So before we talk about it, the binary, and then we look at this example. Okay, so look at the example. So if you have 4 equals 0, something like this, so then we need to look at what is the algorithm. So this algorithm is this the second loop is depend on. Okay, so j is depend on I. So then what we can have, this algorithm. What is this algorithm? So this algorithm is something like this. So this algorithm produces the lower triangle set by 0 number in two-dimensional array. Okay, and for instance, that the example output for n equal 5, what we can see something like this. Okay, so when n equal 5, then we can see that we can write something like the triangle like this. Okay, so the 0 0 0 0. Okay, the start is okay, so anything. Okay, which can be null or something like that. Okay, so this is the algorithm. So then how to analyze this algorithm using table method? Okay, so the using table method is a very simple. Okay, so then first that we fix this 4. So we run this 4 one by one. Okay, and then we analyze that the second loop. Okay, so since that this is the operation, only one operations in this one, only one operation, and then this one we can change. Okay, so the table is something like this. Okay, so when I say, so I is the loop, the outer loop. Okay, so in the outer loop, so we from 0, where I equals 0, then the inner loop is j equals 0, where j less than 0. So j less than 0 is 0 less than 0, it's nothing. Okay, so then the time is 0. When I equal 1, then the 4 is j equals 0 and j less than 1. So that's mean j from j0, 0 is less than 1. It is okay. True. Okay, 0 less than 1. So this is once. But when they increase 1, 1 less than 1, so it is false. Okay, so it should be 1. Okay, something like this. So so if I equal 2, and then for j equals 0, from j less than 2, it should be 2, and etc. until n minus 1. Okay, so n minus 1 is that for j equals 0 until j less than n minus 1, it should be n minus 1 times. Okay, so then finally we have Tn. So the Tn is that we sum of this one. Okay, sum. Okay, sum. So it should be Tn is equal to 1 plus 2 plus 3 plus 4 plus 6 plus n minus 1, which is this is equal to half of n square minus n. How to get this one? So remember that 1 plus 2 plus blah 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 plus n is equal to n times n plus 1 over 2. So if we change n equal to n minus 1, so it should be n minus 1 times n. Okay, n minus 1 times n over 2, it should be something like this. Okay, so this is very simple. Okay, and this time efficiency will is in the big O of n square. Okay, so this is very simple. Okay, now, okay, so since that is very simple, actually, we can use sum actually in here. Okay, so actually we can use sum. Indeed, that we can use something like sum of I equals 0, and this is less than n, so it should be n minus 1. Okay, and this one j is sum of j equals 0, and it should be less than I minus 1. Okay, it should be something like this. Okay, and it should be 1. Single 1. So actually using sum, it's also possible. Okay, so but now we move that with the example that this is the example when so it is in irregular loops. Okay, so something like this. So n is decreasing 2 times. Okay, so what we need to do is that, of course, that we need to create table constructions. Okay, so the table construction is something like this. Okay, so first that we need to count. Okay, so count. You need to check count. Okay, count, and you check n. Okay, and then you check times. Okay, so this is time. So what we can do? So first that count. So when count equal to 1, then n is equal to n. Okay, and there's nothing operation. So since that this is the operations. This is the operations, one operations. Nothing to do, right? So when this is the first count equal 1 and n it's still equal to n, and there's nothing basic operations, so it should be 0, right? Something like this. Okay. So when okay, so but when C1 and 1 and then move to this count, move to this one, so n is greater than 1, of course. Okay, so it should be 1. Okay, something like this. Okay, similar. Okay, so similarly something like this. So first that it should be 0 first time. Okay, since that there's no basic operations, but they can move to 1. Okay, 1 and n is greater than 1, of course, since that n, assume that n is very big. Okay, it's very big. Sorry, and then sorry, and 1. Okay, so this is 1. It's greater, very big, so bigger than n. Okay, bigger than 1. Sorry. So then we have something like this: c equal 1, and then what the times? Okay, so the time is, of course, that time is 1 since it is executed. Okay, so when count 1 and n is greater than 1, it is okay, and do, and this is executed, and this is executed, should be 1. Okay, next move to this one when n is divided by 2, so this is n. Okay, n divided by 2, and then we move again, right? So the count is count plus 1. Count plus 1 is, sorry, so it should be this run and 1, and then produce count is equal to count plus 1. It should be 2. Okay, 2, and then n is n over 2, and move again and over 2, that this will be executed again, and should be in 1 times, and this is become 3. Okay, and n minus 2, it should be n minus 2 over 2. Okay, so it should be 1 time. Okay, and etc. Okay, so and etc. And finally, something like this we will have. So when I count one, it should be n is one time, is accurate, and 1 2 is n over 2, or imagine that n is in here. Assume that n is equal to 2 power to the k. Okay, so then this is 2 power k over 2. It should be 2. Is it something like this? Okay, so okay, sorry about that. I already write. Okay, so this one, assume that n is equal to power to the k, and then should be 2 to power the k over 2. It should be 2 power to the k minus 1, etc. Okay, so and then 3 is n over 4 is 2, or 2 4 is 2 power to the 2, and then it should be equal to 2 power to the k minus 2 again. Okay, and etc. And then until what? So finally, I don't know. Okay, so assume that it should be stopped, for instance, at when it is k times. Okay, at k time it should be uh, n over 2 k minus 1. It should be 2 uh, 2 power to the 1. It should be 2, and then we executed 1, and then when k plus 1, then it should be 1. So since 1, so this loop will be stopped when n equal 1, right? So when n equal 1 and stop, and so there's no basic operation called. Okay, so and then what we can find, that we'll find Tn. Okay, so the Tn is the sum of 1 1 1 1 1. So how many ones we have? So exactly that we have 1 1 1 1 k times, right? So this is equal, the Tn is equal to 1 plus 1 plus 1 plus 1. It is k times 1. Okay, now the problem is that we have a function Tn, but the variable is n actually. Okay, the independent variable is n, but we have k. There's no n here. Okay, so that's the problem. Okay, so the problem now is that we need to define Tn is equal to something with n. Okay, with n. Okay, since that k is the assumptions. Okay, so then what we have, that remember that we used the previous assumption that n equal to 2 power the k, and then what we have, n is n over 2 power the k is equal 1, and then we use logarithm. Okay, actually this is very easy. Use the logarithm, and then what we have, log of n over 2k is equal to log to 1. So where log 1 is going to 0, and then log 2, it should be a over b. It should be log a over b should be log a minus log b, and it should be log to n minus log to k. Okay, so and then we can reverse the positions, that since that this is log 2. Okay, sorry, this is log 2. So log 2 to k should be k, can be in front, k log to 2, it should be log to n, and then log to 2 is 1, and then k is equal to log to n. Then finally, that what we have, the Tn is equal to k is equal to log to n, which is the PO of log to n. Okay, okay, so I think this is very simple. So this is a very simple example that we can analyze very complicated algorithm, and then we can find how uh, we can find the Tn. Okay, so the functions of the time complexity. Okay, so then this is the homeworks for all of you. So this is we have a two homeworks. So then this one and this one. Okay, so try by yourself. So find out what the Tn of those or these algorithms. Okay, so I think that's all. Okay, thank you very much for your attention. See you again in another video. Okay, So see you. Goodbye.